Hey, Matt Roscoe here at the University of Montana in our course Math 326 Number Theory. Here's a lecture on Chapter 6-2, the Mobius inversion formula. So let's get to it. So the first thing I want to do is introduce you to the Mobius mu function and then talk about, well, is it a multiplicative function? If it is, we can work with it a little bit easier. And then go ahead and expand our understanding of that. Once we've expanded our understanding of the Mobius function, we'll introduce you to the inversion formula and talk about its implications for some number theoretic functions we're already familiar with, that is tau and sigma, and then leave you with the Merton's conjecture and a famous, I guess, story from the history of mathematics about this function. So here is the definition of the function. It says for a positive integer n, define mu by the rules. Now it takes on one of three values you can see here, but it's actually one of two values. So it's always 1 if n is equal to 1. So there's a special case here. If we input 1 into the function, the Mobius mu function, we get back 1. It always reports 0 if p squared divides n for some prime p. And then it reports negative 1 raised to the r if n can be written, of course, if it's a square-free prime factorization, then it has some list of primes all raised to the first power, so p1 times p2 up to pr, where pi are just, they're all distinct primes here. So it reports some negative 1 or positive 1, I guess, at that last case, depending on whether you have an even or odd number of prime products that all have power 1. Well, let's take a look at this. Let's compute mu of n for the first 20 integers. I think that gives you a good idea what's going on here. So let's see here. Okay. So let's see, if n is 1, then mu of n, you know, it might make sense to leave the prime decomposition in the middle. So position and then mu of n. Well, we know that 1 has no prime decomposition because it's neither prime nor composite, but by the definition of mu, the special case for 1 is given the value of 1, mu of n. 2 has prime decomposition of just 2, so that would be a negative 1 because there is no square number that divides 2, and we just take, I guess, negative 1 raised to the power 1, and we get a negative 1. 3 is the similar, so it's 3 to the first, it's negative 1. 4 is our first non-square free, I guess, prime decomposition. So it reports a 0 because some p squared divides 4, and that p squared is 2 squared. 5, of course, is just 5 to the first, so it'd be negative 1. 6 is 2 times 3, each to the first power, so no square divides it, but we raise negative 1 to the 1 plus 1 or 2 power, so you get a 1 there. 7 is just 7 to the first, so it's negative 1. 8 is going to be 2 to the third, but some p squared does divide 8. That p squared is 2 squared, so it reports a 0 here. 9 is 3 squared, reports a 0 here. 10 is a 2 times a 5, so it'll be very similar to 6, 2 times 3. So we raise negative 1 to the 2 power, and we get a 1. 11 is just 11 to the first, so it's a negative 1. Let's see, 12 is 2 squared times 3. It has a p squared that divides it, so 0. 13 is just 13 to the first, so it's a negative 1. 14 is 2 times 7, so it's a positive 1. 15 is 3 times 5, that's a positive 1. 16 is 2 to the fourth, 2 squared divides it, or 4 squared divides it. 17 is just 17 to the first, so it's a negative 1. 18 is going to be written as what? 2 times 3 squared, so that's a 0 because p squared divides it. 19 is just 19 to the first, So that's going to be a negative 1. Let's see, 20 is going to be 2 squared times 5. Since there's a p squared that divides it, it's 0. So there you have the values of mu for the first 20 integers. What do we... I would just ask you to take a look at the table and ask yourself a few questions about it. I mean, one thing you should ask is it multiplicative? And what would you look at to test to see if it's multiplicative? So one thing you could test is you could test some function whose product is known and who's on the table. So, excuse me, some value whose product is known. So 6 might work out nice because 6 is 2 times 3. And it does look like the mu function evaluated at 6 is just the mu function evaluated at 2 and 3 multiplied together. To take a look at another, I guess, example of that. I don't know, what's another example of that we could do? Maybe 20 would be interesting because 20 has a 0 involved, and so does 4 and 5. So it does look like the product of the value at 4 and 5 works here. Remember, for it to be multiplicative, the two factors have to be relatively prime. 4 and 5 are relatively prime. 2 and 3 are relatively prime. We could take a look at 15. 15 is 3 and 5, and they're relatively prime. Here you get a 1, 3, and 5, negative 1, negative 1. So you get a. So it does appear, at least at first glance, that it's multiplicative. 10 would be another one we could check. So 10 would be 1. 2 and 5 are relatively prime. 2 is a negative 1. 5 is a negative 1. So yeah, it seems like we're getting a multiplicative function there. So we say yes to this question. Mu of n does appear to be multiplicative, and indeed this is the first theorem in the chapter. So let's go ahead and prove that that the Mobius mu function is actually a multiplicative function. So let's see. Our hypothesis is that mu is multiplicative. That is, mu of m times n is equal to mu m times mu n whenever the GCD of m and n is equal to 1, right? So here's our proof. This is kind of an interesting proof, and I'll just call your attention to it because it might be helpful, this format, in your homework, especially in problem number 7. Let's see. So look at the case when p squared divides... Oh, I misspoke. This isn't the one that's helpful on problem 7. I'll draw your attention to that in a minute. When p squared divides m, or p squared divides n. So then p squared must divide mn, right? The product. If it divides one of the two, then it has to divide the product. What does it imply? Well, this implies that mu of mn is equal to 0 because p squared divides m and n, and mu of m times mu of n must be equal to 0, and that's because one of the two has to be valued at 0. So mu of mn must be equal to 0, must be equal to mu of m times mu of n. So in this case, it makes perfect sense, right? If you've got a zero in a product, you're going to have a zero valued function, and this one's going to be zero valued because of the fact that p squared divides 1 of m or n. Okay, so that's one case. Now look at the case where neither p squared divides m or p squared divides n for some p. So I guess what we're saying is that m and n have to have some Mobius mu function value of either 1 or -1. So the kind of the more general case. So yeah. Then both m and n are square free. In their prime decomposition. Thus, we can write m as some sequence of primes, p1 times p2 times, I don't know, all the way up to pr. And we can write n as some sequence of primes, let's call it q1 times q2 times all the way up to some qs. And since the GCD of m and n is 1, all the PIs and QJs, let's call them, are what, distinct, non-equal, I guess distinct. Thus, if we multiplied m times n, what we get is we just get what, p1, p2, all the way up to pr times q1 times q2, all the way up to qs. So if we applied the Mobius function then to this, we know what to do, right? It's Mobius mn will be the Mobius value of Mobius function evaluated at this prime number factorization. q1 times q2 times all the way up to qs, which is just going to be, well, you know, it's however many number of prime factors we have, it's going to be -1 raised to that power. So there'll be r of these and s of these, so it must be r plus s power, which is the same thing as -1 to the r power times -1 to the s power. And I would do this right here, but it's getting pretty low, so, well, I'll do it right there. I guess it's fine. So that would be mu evaluated for m times, sorry, ran out of lead right at the punchline. Mu evaluated for n, and that concludes the proof, right? Because what we've seen is that mu for the product is equal to the product of mu evaluated for each of its factors, so long as the two factors are relatively prime. So indeed, it is a multiplicative function. It has to do with addition of exponents, really. And then let's take a look at this expanded. So it says that for each positive integer n greater than 1, then the sum of the divisors of n evaluated at mu is equal to 1 or 0. It's equal to 1 if n is equal to 1. It's equal to 0 if for any n greater than 1. So let's take a look and see if we can really understand what this means here. So just to get a sense of it before we try to prove it. So we're saying that this guy, um, f of mu, I guess, which we're going to call n, the sum of all the across all the divisors of n, mu of d, um, and we're saying that it's equal to 1 for n equal to 1, or 0 for n strictly greater than 1. So this is kind of the question mark right now. Well, let's just make sure. F of 1 would be it would be the sum of all the divisors of 1 of mu evaluated at those divisors. Well, that's pretty easy. That's just mu of 1, and that's equal to 1. So check mark there. When n is 1, then the sum of all the divisors of 1 is just 1. But what about if it's something a little bit more complex? What if we evaluated this at 10? Then it would be the sum of all the divisors of 10 of mu evaluated. So let's see, the divisors of 10 are going to be 1, 2, 5, and 10. So it would be mu of 1 plus mu of 2 plus mu of 5 plus mu of 10. And that seems like a pretty crazy thing. But if I had my board work, I could sort of just add these up. Mu of 1, of course, is just 1. Mu of 2 is negative 1. Mu of 5 is negative 1. And mu of 10 is positive 1. And indeed, that is 0, which checks out here. I don't know. Should we try a couple others? I don't know. How about mu of 12? Or excuse me, big F of 12. That will be the sum of all the mu of d's, where the divisors run across 12. So let's see. So the divisors of 12 are 1, 2, 3. Let's see, so it would be mu of 1 plus mu of 2 plus mu of 3 plus mu of 4 plus mu of 6 plus mu of 12. So what do we get there? 1. This is negative 1. This is negative 1. This is a 0. This is positive 1. And this is 0. So I see the 1 and positive, negative, and negative. Again, we get 0 here. So I don't know if this is somewhat surprising to you, but it was to me the first time I saw it. And when we count up, I guess the mu evaluated across the divisors of a number, that the sum is always 0 unless that number happens to be 1. So let's go ahead and prove that. So I'll let the hypothesis be on the slide here. So let's go ahead and consider this function, big F of mu of n, which is the sum across the divisors of n of mu of d. So this is the one I wanted you to think about for problem number 7 in your homework. So the proof for this particular theorem, I guess, is somewhat helpful in form. Okay, so let's see. When n is equal to, let's say, some p to the k, here we get tau of n equal to k plus 1, right? So the total number of divisors we get here are k plus 1, right? Every single power of k is the divisor of n as well as 1. So k plus 1 is tau of n. And I guess that's because the divisors are 1, p to the first, p to the second, all the way up to p to the k, right? So what can we say here? We can say that f of mu of p to the k, right, will be, I guess, this mu evaluated across these divisors, right? Well, let's just go ahead and write it out. All the divisors of p to the k of mu evaluated at those divisors, which will be mu of 1 plus mu of p plus mu of p to the second plus all the way up to mu of p to the k, right? So let's just think about each one of these divisors and what their mu value will be. Well, mu of 1 is always equal to 1. Mu of p will always be equal to negative 1, right? Mu of p squared will be valued at 0, right? Because it's got a square that divides it. And in fact, all of these in between will have a square that divides it as well as this last one, right? So these are all zeros, and that's because some p squared divides the number. So what do we see here? We see that for strict power of prime, you're always going to get a sum that's 0. It's just the 1 plus the 1 power that's square free. So if we now expand that, I mean, this is the source of the 0, I think. If we expand that now to consider some m in the positive integers, and let's let it not be equal to 1, then what can we say? Then m has some prime factorization, right? And let's generally write it as prime factorization. Say it's p1 to the k1 times p2 to the k2 times all the way up to, I don't know, pr to the kr. And let's think of now evaluating f mu of m. So f mu of m is going to be f of, well, this p1 to the k1, p2 to the k2, pr to the kr. Now, we know that mu is multiplicative, right? So big F is multiplicative too, right? We proved that in the last chapter. So this would be f of p1 to the k1 times f of p2 to the k2 times f of pr to the kr. And I'll just say, since mu of n multiplicative, and I guess we should also say that each one of these are relatively prime, and GCD of pi, pj equal to 1, f multiplicative also. But each one of these guys we know to be 0 because each one of these guys is of this form, right? So this is a 0 times a 0 times a 0. So here we get 0 as our answer, which is what we wanted to show. So indeed, the sum across the divisors is always valued at 0, unless, of course, the number in question is 1. Oh, kind of an interesting property of this Mobius mu function. Let's go ahead and give an example here. Well, what would be the sum of the divisors across 12 of mu of d? I think we already did that, didn't we? So here we did it right here. We got a 0. Oops, sorry, I didn't show that on the overhead, but I think we already did that in the previous overhead. So here it is. Here's the big Mobius inversion formula, and If we say it's a broad formula that incorporates the Mobius mu function, it says that if f and f, so big F and little f, are two number theoretic functions that are related by this formula, big F of n is, of course, the sum across all the divisors of little f of d. Then we could say that f, the little f of n, is equal to the sum across all the divisors of n of mu of d, big F of n divided by d, or the sum across all the divisors of n of mu of n divided by d times big F of d. So a few things to note here is that this is called the Mobius inversion because what we really see inverted here is it's almost like it's an inverse. It allows you to solve for little f of n as a function, given information about big F of n of a function and mu and the Mobius mu function.